If an equipment grounding conductor, or EG, is installed, it must adhere to the size requirements outlined in the National Electrical Code, specifically Section 250.122. This applies even if an EGC is not strictly required by the code for a particular installation. When working with a 208-volt, 60-amp feeder in a grounded 1-inch electrical metallic tubing, or EMT conduit, and deciding to install an EGC, it is crucial to correctly size the conductor. The requirements in 250.122 are based on the overcurrent protective device protecting the circuit. In this instance, we will need to determine the appropriate size of the equipment grounding conductor based on the 60-amp overcurrent device protecting the 208-volt feeder. Refer to NEC Table 250.122 to find the minimum size of the equipment grounding conductor. The table provides guidance on the minimum size of copper, aluminum, or copper-clad aluminum conductors based on the rating of the overcurrent protective device in the circuit ahead of it. For a 60-amp overcurrent device, Table 250.122 typically requires a minimum of a number 10 American wire gauge or AUG copper conductor or a number 8 AWG aluminum or copper-clad aluminum conductor as the equipment grounding conductor. Always consult the latest edition of the NEC to ensure compliance with the most current requirements. If the ungrounded conductors are increased in size for voltage drop, the equipment grounding conductor must be proportionally increased in size according to 250.122b. This ensures that the ground fault current carrying capacity of the EGC is adequate. The purpose of the equipment grounding conductor is to provide a low impedance path for fault current to return to the source. This low impedance path facilitates the operation of the overcurrent protective device, such as a circuit breaker or fuse, which then clears the fault and protects the equipment and personnel from electrical hazards. If the EGC is not properly sized, it may not be able to effectively carry the fault current, which could result in a higher voltage on metal parts of equipment, creating a shock hazard and potentially preventing the overcurrent protective device from operating. The equipment grounding conductor connects the metal parts of electrical equipment, such as enclosures, conduit, and motor frames, to the grounding electrode system at the service. This connection ensures that if a fault occurs, the fault current will have a low impedance path back to the source, allowing the overcurrent protective device to quickly clear the fault. Proper grounding and bonding are essential components of electrical safety. Bonding refers to the connection of metal parts to create a continuous electrical path. This ensures that all metal parts are at the same electrical potential, minimizing the risk of electric shock. Grounding and bonding work together to provide a safe and reliable electrical system. In the specific scenario of a 208-volt 60-amp feeder in a 1-inch EMT conduit, it is important to verify that the EMT conduit itself is properly grounded and bonded. EMT conduit can serve as an equipment grounding conductor under certain conditions, as outlined in NEC Section 250.118. However, it is still common practice and often recommended to install a separate equipment grounding conductor within the conduit, especially for sensitive electronic equipment or where a higher level of grounding reliability is desired. When installing an EGC in the EMT conduit, it is important to ensure that all connections are properly made and tightened. Loose connections can increase the impedance of the grounding path, which can reduce its effectiveness. Use appropriate connectors and fittings that are listed for grounding purposes. In addition to sizing the EGC according to Table 250.122, consider other factors such as the length of the circuit and the potential for voltage drop. If the circuit is long, it may be necessary to increase the size of the EGC to compensate for voltage drop. The NEC provides guidance on how to calculate voltage drop and how to size conductors accordingly. Always consult with a qualified electrical professional if you have any questions or concerns about grounding and bonding requirements. Electrical work can be dangerous, and it is important to follow all safety precautions and code requirements to protect yourself and others from electrical hazards. In summary, when installing an equipment grounding conductor in a 1-inch EMT conduit with a 208-volt 60-amp feeder, the EGC must be sized according to NEC Section 250.122. Refer to Table 250.122 to determine the minimum size of the conductor based on the rating of the overcurrent protective device. Ensure that all connections are properly made and tightened, and consider other factors such as the length of the circuit and the potential for voltage drop. Always follow all safety precautions and code requirements to protect yourself and others from electrical hazards. Understanding the role of the equipment grounding conductor is critical for ensuring electrical safety. The EGC provides a low impedance path for fault current, facilitating the operation of overcurrent protective devices and minimizing the risk of electric shock. By properly sizing and installing the EGC, electrical systems can be made safer and more reliable. The NEC provides comprehensive guidance on grounding and bonding requirements. Staying up to date with the latest edition of the NEC and understanding its provisions is essential for all electrical professionals. In addition to the specific requirements for sizing the EGC, the NEC also addresses other aspects of grounding and bonding, such as the types of grounding electrodes that are permitted, the methods for connecting to the grounding electrode system, and the requirements for bonding metal parts of electrical equipment. Proper grounding and bonding are essential for protecting electrical systems and personnel from electrical hazards. Ignoring these requirements can lead to serious consequences, including electric shock, fire, and equipment damage. Always consult with a qualified electrical professional if you have any questions or concerns about grounding and bonding requirements. Electrical work can be dangerous, and it is important to follow all safety precautions and code requirements to protect yourself and others from electrical hazards. Ultimately, compliance with NEC Section 250.122 and other applicable grounding and bonding requirements is essential for ensuring the safety and reliability of electrical systems. When working with electrical systems, prioritize safety above all else. Always follow all safety precautions and code requirements, and consult with a qualified electrical professional if you have any questions or concerns. In practical application, consider a scenario where a 208-volt motor is fed from the 60-amp feeder. The motor enclosure must be connected to the equipment grounding conductor to ensure that any fault current can safely return to the source. The size of the EGC running with the circuit conductors to the motor must be sized according to Table 250.122, based on the 60-amp overcurrent protection. This is crucial in preventing electrical shock hazards if a fault occurs within the motor. Furthermore, the connection between the EGC and the motor enclosure must be secure and properly made using listed connectors to maintain a low impedance path. In situations where the feeder supplies multiple loads, each load must have its own equipment grounding conductor sized according to its respective overcurrent protection, adhering to the principles of 250.122. This ensures that each piece of equipment is adequately grounded, providing a safe path for fault current. Regularly inspect electrical systems to verify that grounding and bonding connections are intact and in good condition. Corrosion, loose connections, or damaged conductors can compromise the effectiveness of the grounding system. Addressing any issues promptly is vital to maintaining the integrity of the electrical system. The NEC is continuously updated to reflect advancements in technology and address emerging safety concerns. Staying informed about the latest code changes is essential for electrical professionals to ensure that their work complies with current standards. Regularly attending training sessions and participating in continuing education programs can help professionals stay up to date with the NEC. Moreover, consider the impact of harmonics on the grounding system. Harmonic currents can increase the current flowing through the equipment grounding conductor, potentially overloading it. If harmonic currents are present, it may be necessary to increase the size of the EGC to accommodate the increased current. Consulting with an electrical engineer is recommended when dealing with harmonic currents to ensure that the grounding system is adequately designed. In some cases, an isolated ground system may be used to minimize the effects of noise and interference on sensitive electronic equipment. An isolated ground system provides a separate grounding path for the equipment, isolated from the building's normal grounding system. The NEC provides specific requirements for isolated ground systems, which must be followed to ensure safety and compliance. Remember that the effectiveness of the equipment grounding conductor depends on the quality of the connections and the overall grounding system. A properly designed and installed grounding system is essential for protecting electrical equipment and personnel from electrical hazards. Electrical codes and standards are developed to minimize risks associated with electricity. Compliance with these codes is not only a legal requirement, but also a moral obligation to ensure the safety of people and property. Always prioritize safety and follow best practices when working with electrical systems. Electrical safety audits can help identify potential hazards and ensure that the electrical system is in compliance with applicable codes and standards. These audits should be conducted by qualified professionals who have expertise in electrical safety. When designing electrical systems, consider the potential for future expansion and the impact on the grounding system. Ensure that the grounding system is adequately sized to accommodate future loads and that any modifications or additions to the system are properly grounded and bonded. Effective communication is key to ensuring electrical safety. Electrical professionals should communicate clearly with their clients about the importance of grounding and bonding and the potential risks associated with electrical hazards. Clients should be educated about how to identify potential electrical problems and what to do in case of an emergency. By promoting electrical safety awareness, we can help prevent accidents and protect lives. The selection of appropriate grounding and bonding methods should be based on a thorough understanding of the specific application and the potential hazards involved. Factors to consider include the type of equipment being grounded, the environmental conditions, and the applicable codes and standards. In addition, using high-quality materials and components is essential for ensuring the reliability and longevity of the grounding system. Cheap or substandard materials can compromise the effectiveness of the grounding system and increase the risk of electrical hazards. Investing in quality materials and workmanship is a wise investment in electrical safety. Training and education are essential for promoting electrical safety. Electrical professionals should receive comprehensive training on grounding and bonding principles, as well as the latest codes and standards. Ongoing education is also important to stay up to date with advancements in technology and changes in the electrical code. By investing in training and education, we can create a more knowledgeable and skilled workforce that is better equipped to ensure electrical safety. The equipment grounding conductor provides a path for fault current to flow back to the source, allowing the overcurrent protective device to trip and de-energize the circuit. This helps to prevent electrical shock and fire hazards. The impedance of the grounding path should be as low as possible to ensure that the fault current can flow quickly and easily. High impedance can limit the flow of fault current and delay the operation of the overcurrent protective device. Proper grounding and bonding are essential for minimizing the risk of electrical hazards. Ignoring these requirements can have serious consequences. When working with electrical systems, always prioritize safety and follow all applicable codes and standards. In summary, the proper sizing and installation of the equipment grounding conductor are critical for electrical safety. Compliance with NEC Section 250.122 is essential to ensure that the EGC can effectively carry fault current and protect equipment and personnel from electrical hazards. Remember to consult with a qualified electrical professional if you have any questions or concerns about grounding and bonding requirements.